enable the option. So the key to this regression first is basically what is called the maximum likelihood estimate. Maximum likelihood estimate is an estimate. So basically we are looking at an estimation. So this comes under, basically you can also say that this is coming from, it also comes under the topic of estimation theory. So this is from probability, we go to statistics. Oh, what is that we are doing? Let's see now. Let us say that you're making some measurements. Okay. So there is only, now you're considering that y is a function of x. Okay. This is your independent variable. This is a dependent variable. It's a one variable problem. Okay. To make matter simple, let us say, yeah, are you able to read what I'm writing on the board?
Yes, sir.
Thankfully, I did not ask this question in the last class. Okay, so to make matter simple, let us say y equal to ax plus b. Okay, now the question before me is very simple. I have a tabular column of x versus y. So x1, x2, x3, blah, blah, blah. y1, y2, all this is available. Now, I want to fit or regress the straight line to this data so that I have a very powerful tool at my disposal, which means once I estimate A and B using whatever funda, using any ideas which I've got from estimation theory, this estimation theory could be guided by principles of probability, statistics, whatever. Somehow I'm able to estimate. Then if you tell me the value of x, I'll be able to give you the value of y. Of course, we can do quality control. We can say how good this correlation, how bad is it, what is the likely error and all that. That we can do. So the AB are called the parameters of the model. What is this model? In this case, the model is a linear model. So don't be bamboozled if the computer science person says model. It's a linear model. Parameter is just here A and B. Okay. So now we want to get A and B. So the maximum likelihood estimate of A and B. This is what we are. Therefore, now we start with some fundamental premises. For various values of x, I am measuring the value of y. Okay. For various values of x, I am measuring the value of y. Okay. I am measuring the radar reflectivity. From that, I am trying to get the rain, let us say. Okay. This is the radar reflectivity. It is the rain. I want a correlation. Of course, it is not a linear correlation. And just for argument's sake. So this is my reflectivity. This is my rain. Now I should be able to give what is my error in the reflectivity. I know the instrument. I talk to the manufacturer. I can do some basic preliminary results and then experiments, and I can find out what is the error associated with x, with the measurement of x. Now, if the errors are all normally distributed, then we can say that we can use the principles of the normal distribution and try to proceed, try to go somewhere. Where is that somewhere? That is what is the maximum likelihood estimate. Listen to this carefully. Let us assume that all the measurements are made with the same instruments and the measurements error follow Gaussian with a standard deviation of sigma. This is the error the standard deviation associated with the measurement of x. Okay. Now if we propose a the error associated with the measurement of y. Okay, not x. So let's say let's not worry about this. So the error is in y. The error can also be in x.
If the error is in X, you have to regress X in terms of Y. Okay. So the funda is very simple. We cannot allow errors in both the things. Then it will become there'll be a sigma 1, sigma 2. It will complicate things. Okay. So let's get back to this. If you propose a linear model for y equal to f of x, we have y equal to ax plus b. A and b are the parameters of the models and are as yet unknown. The goal of the linear regression is to be able to get A and B if a data set of y against x is available. Okay. Now, see, now you can see, sir, suppose you say, sir, one time you are saying error in x, error in y, how to believe you? Now look at this. Okay. Pradeep, Kia. Okay. Thank you. So I will lock it and keep it. Thank you. Tomorrow. Okay. Okay. Y fit. If y fit equal to ax plus b, the probability of getting y based on the Gaussian distribution. This is where we are connecting the probability. Now we are saying that. So I'm assuming a set of parameters a, b. What is the probability that I will get y1, yi is basically 1 by root of 2 pi sigma square e to the power of now we had x minus mu whole square in the Gaussian distribution. Now that is the error. That is a deviation from the mean. Now we are saying that instead of the deviation from the mean, the difference between the model prediction and the data, that is my error. Okay. Now I have a table of so many values. Okay, I have a table of so many values. So the probability of getting P of y1 given AB is called a conditional probability. This is a conditional probability. 2 pi sigma square. So this is P of y1 is written. Okay. So you can call it as P1. You call it as P2. E to the power of minus y2 minus ax2 minus b by 2 sigma square. There should be a square here. Okay. Like that, I can go up to Pn. Now comes the question, what is the probability that I will simultaneously get P1, P2, P3, P4, P5, P6, P7, P8? Okay. That will be a joint PDF, joint probability density function. So common sense tells you that it must be the product P1, P2, P3, P4, and so on. Okay. If I toss a coin, what is the probability that continuously I will get 3 times? If I 3 times in a row, I will get only head. So first time I have to get head, that is half. Second time also I have to get head, that is half. Third time also I get that's half. It is half into half into half. Correct? So it is that the joint probability density is basically probability is basically P1 into P2 into P3 into P4. Now that the joint probability, or you call it as a total probability L, because statistics terminology, probability terminology, they use this. Now if you do this, it basically turns out that L is nothing but L is what is L? L is P of y1, y2, blah blah blah, yn for that AB. Okay. Now this is nothing but all the 2 pi, 1 by 2 pi sigma square are going to come. Okay. So this will be 2 pi sigma square n by 2. And then this should be e to the power of minus sigma I equal to 1 to n yi minus axi minus b whole square minus 2 sigma square. Now, if you take z equal to minus 2 ln of L, the first will be this. This is a constant term because sigma square is already predefined. We know what the errors associated with the measuring instruments are. So this will be basically z equal to what is written there, n of ln of 2 pi sigma square plus sigma I equal to 1 to n yi minus axi minus b whole square by 2 sigma square. Now we have to find out
Now the whole thing is you have to max the L. So what is the funda of max the L? Max the L means what is that value of A and B which will maximize the L? That is the solution to the problem. There are various ways of approaching the problem. But first you have to state the problem. To state the problem is for a given value of A and B, I can put it into that model and calculate the Y and then calculate the error. What is the combination of A and B which will max the L? Since Z equal to -2 ln L, we have to look at min of Z. Max is maximization. So the min of Z is, when will this Z be minimum? This is, once you take the sample in sigma square, this is no longer going to affect the problem. Therefore, Z will be minimum if this is the minimum. This is nothing but minimization of least square. So the minimization of the least square between the model and the data is nothing but the maximum likelihood estimate. Correct? So the maximum likelihood estimate is basically the least square regression for the simple straight line. Did you get the idea? Did I explain it properly? Can somebody respond? Can somebody tell me? Is it okay?
Yes, sir.
Yeah. All right. Okay. Now let us look at a practical example in atmospheric science. I keep talking about the radar reflectivity. You know that if the reflectivity is very high, if you send a signal, let's say from the ground, upward looking radar, if the reflectivity is very strong, that means there's a strong rain which is reflecting the radiation. If the reflectivity is 0, that means there is no rain. So the reflectivity and rain are related by what is called the Marshall-Farmer distribution. You don't have to worry about that now. So you can Google it up later. Some people who are working in rain will know this. So this is called the Marshall-Farmer distribution. Okay. So the rain rate is given by A Z to the power of B. Sir, you taught us only least square regression. How will you make it? How will you make it least square? Linear least square? Can somebody tell? The answer is on the slide itself. Can somebody tell me? How do you make it into a straight line? Hello? I hope people are there. Just tell me. Jayant, Soumya, Walter.
Sir, we are here, sir.
You apply natural log on both sides.
Apply natural log. There you are. Ln RR equal to ln A plus B ln Z. Okay. So Y to A plus BX. There you are. So take your reflectivity, take the ln of it and make it to X. Take your rain rate and make it to this. Now fit the parameters A and B. Okay. Now this is the example we are going to study now. If you can pull out your calculators, or if you're good with the Excel in your computer itself, it should be fine. Okay. Now I will, before going into the example, I want to look at other forms which can be where linear least squares can be used. Suppose the function is of the form y equal to a plus bx1 plus cx2. To estimate a, b, c, what you do is, so if it is a linear function in two variables. Okay, y equal to a plus, what did I write? Bx1 plus cx2. So what we can do is sigma yi minus a minus b x1i minus c x2i whole square. So I equal to 1 to n. The sum of the square of the residual is called s. So you can put dou s by dou a equal to 0, dou s by dou b equal to 0, dou s by dou c equal to 0. So this is 3 equations and 3 unknowns. Okay, can be solved. So even if there is a linear combination of variables, as many variables as you want, this can be linearized. Okay, let's proceed further. If it is a quadratic also, you can say dou is y equal to a plus bx plus cx square. You can take dou s by dou a equal to 0, dou s by dou b equal to 0, dou s by dou c equal to 0 of the residual, sum of the squares of the residual, minimize that. 3 equations and 3 unknowns, solve for a, b, c. So you're able to get the parameters of the distribution, whether it is a and b in the case of Marshall-Palmer, or a, b, c in the case of linear least square and 2 variables, or a, b, c in the case of a polynomial regression with power 2. In all the cases, the linear least squares is working. Okay. Now the other forms, for example, if it is y equal to ax to the power of b, this is the Marshall-Palmer. So ln of y equal to ln of a plus b ln x. So this is possible to linearize. Okay. Y is equal to ax plus ax divided by b plus x. Okay. What you do now is take 1 by y. 1 by y will be b plus x by ax. So you can do some jugad here. So b by a into 1 by x plus 1 by a. Okay. So 1 by y equal to some c into x plus d. That's it. So finally, so this was looking like a scary function. So this is called linearization. So don't think that all the forms can be linearized. I'm just giving you some, I'm giving you some hope where many forms which look menacing, which look threatening, can be converted to the linear forms. Okay. Now let's go into a little bit of matrix algebra. So the linear least squares, if you've got many variables, it's good to know linear algebra, because the linear least square is very compatible with linear algebra. So what you have to do is, basically, I have to tell you the equations. Okay. So the maximum likelihood head estimation is nothing but least square regression. Huh? Okay, so S. Okay, so equation number 1, equation number 2, dou S by dou B. The equation correct? Are the equations correct? Can somebody confirm? Huh? Can you confirm? Excuse me?
Yes, sir, it looks correct, sir.
Looks correct. Therefore, if you take this, so this is nothing but A can be taken out, A sigma xi square plus B sigma xi equal to sigma xi yi. Then this one is A sigma xi plus B into B1, B2, this is basically NB. Huh? B repeats as many times as so many N's are there, as many B's. So NB is basically equal to sigma YA. Okay. So I'm just doing sigma YA. So these two are negative signs. So I can take it to the other side. A sigma xi Bn equal to sigma YA. Okay. Now this can be written in a very compact matrix form like this, correct? So you can just say sigma xi square, sigma xi n operating on the parameter vector AB is nothing but your sigma xi yi and sigma yi. Yeah, there you are. That's it. Okay. So this is a very nice compact notation. Now, this can be written as. So this can be written as Z transpose T operating on A equal to Z transpose T operating on Y. Okay. Now don't get scared. I will explain to you what is this. So the A is the parameter vector. Okay. Z transpose is Z is basically x1 to xn 1 1 1 1. Okay. So Z transpose is basically x1 xn 1 1 1. And Y is nothing but the Y is a column vector. Okay. Now, if you put it in this form, so you can easily see that. Let's do that. I'm having the cursor here. Can you see this? I'm placing the cursor here. Is everybody with me?
Yes, sir.
Yes, sir.
So the first term is x1 square plus x2 square plus x3 square, x, that is sigma xi square. That's what I've written here. Then if you go to the other term, x1 plus x2 plus x3 plus x plus blah blah, that is sigma xi. Other one again from 1 x1 x2 x3 is sigma xi. Then 1 1 1 1 1 1 into 1 1 into 1 1 into 1 n times is n. So this is basically sigma xi square sigma xi n, and Z transpose T operating on Y is nothing but x1 y1 x2 y2 x3 y3, therefore sigma xi yi. The other one is just y1 plus y2 plus y3 sigma yi. So this form we already, so I erased it. This form we already got. Therefore, what you got by linear least square, the equations are nothing but Z transpose T. Z operating on A is Z transpose T operating on Y. What is the big deal, sir? The big deal here is you can use a highly advanced field like linear algebra to get your, use matrix algebra, use matrix inversion, Gauss elimination, Gauss-Seidel elimination, what have you stuff, and then crack the problem and get the parameter vector straight away. If that is what you want to do, you can straight away get AB. Suppose there are 100 parameters, you can do Gauss-Seidel method, and you can get all the vectors of the parameter, all the parameters of the vector, and so based on the data is the column vector Y, and the Z transpose T is Z is basically, please note that Z is basically on the independent variable and Y is basically on the dependent variable. A is the parameter which you want to find. So you can just say that A is nothing but Z transpose T is Z inverse of Z transpose ZY. Okay, I come again. So A is nothing but Z transpose T Z taken to the right hand side to inverse of Z transpose T Y. Okay, so therefore linear least squares is eminently solvable using matrix algebra. So please keep, therefore, please see that how many cousins, how many friends now it is brought out from data science, and this thing we say that we wanted to do statistical analysis. Then we went into the laws of probability. Then when you did that, when you applied the Gaussian to all the data points, you are marrying probability with statistics. Now, after you got the regression equations, then you figured out that the maximum likelihood estimate is the same as the least square regression. Once you did least square regression, we figured out that it can be written in a matrix form. Once it is written in a matrix form, advanced tools available in maths from linear algebra can be used. So already we brought on board so many friends and cousins, and then we're already building up a case for heavy use of data and statistics and probabilities. Okay. Now, strategy 1. Sir, why should I minimize the least squares? Okay. Good question to ask, but what is the answer to that question? Suppose you say that, no, sir, I want to minimize only this. Minimize sigma yi minus axy. I equal to 1 by 1. So this is the R. Sir, I don't like the least squares and all that, I'll minimize the R. The problem here is, if you have 4 points like this, if there are 2 lines A, if there are 2 points 1 and 2, okay, then any line other than the vertical will actually reduce the S to 0, because large positive errors will be cancelled by large negative errors, and it is not possible for us to get a unique line. But then this is from common sense. You don't like to use common sense. Agreed. Go and do the dou S by dou A equal to 0. It will say sigma xi equal to 0, which is meaningless, absolute trash. Then it will also say dou S by dou B equal to 0, n equal to 0. Then you have to surrender, and it is a give up scene. Okay, you can't proceed further at all. So strategy 1 is tulped. It has to be removed. Now, strategy 2. No, sir, I'm smart. I'm a big fan of modulus. Okay, so you just say I want to do the modulus. Okay, oh, looks smart, huh? It looks nice. Now let us see what happens. When you do this, consider 4 points 1, 2, 3, 4. Suppose I join 1 and 3, it gives a line, and 2 and 4, because with 2 points I can get a line. Funda is any line between the 2 lines will minimize S. Okay. Again, we have to have a problem, unique solution. You can't give me various values of A and B for the Marshall-Palmer. If there are various values of A and B for the Marshall-Palmer, are you telling me that with one radar reflectivity I can get any rain? Is that truth? Nothing could be farther from the truth than this. Therefore, the problem is not with the radar. The problem is with your mathematics, with your fundas. Therefore, this modulus of R would simply not work. All right. Now, minimize the maximum distance. Suppose there are 5 points, 1, 2, 3, 4, and 5 I have not marked. And now you say that I want to minimize the maximum distance from any point to the target line. Common sense tells you that the best thing would be to get the line 2 and then consider point 1 as an outlier and throw him out. But now you want to pacify everything. You want to draw a line 1, which minimizes the maximum distance from any point, which means you're compromising. You are saying that one disagreement or dissent from that stupid point which lies outside is very powerful. He or she has got the veto power. It also happens in meetings, right? Whoever shouts the most is whatever opinion he or she has, the meeting outcome will be based on that. So the outlier is a problem. So the best thing is, if you're a good scientist, remove data cleaning. You'll remove that point and then proceed with the other 4. Or if you have time, you'll repeat the experiment and get the point again. Therefore, minimizing the residue does not work. Minimizing the mod of the residue does not work. This is called the minimax. Minimizing the maximum distance. Okay. It is very much used in decision theory. Minimizing the maximum loss, maximizing the minimum gain. So this is minimax condition. It is basically used in decision theory. Okay, you know the prisoner's dilemma. You know there is a very famous problem in game theory called prisoner's dilemma, where 2 prisoners are in 2 different cells. Somebody has committed a crime. One of them is lying. Then, if they tell the truth, they will get this much punishment. If they don't tell the truth, they will get double punishment. Whatever. What will they tell? Then both of them will lie or something. So this is called. If you've studied this results in a solution called the Nash equilibrium. Okay, and Nash is the subject of the movie The Beautiful Mind, right? So Nash was a great mathematician. So he also founded the Hungarian method in operations research, the Hungarian method for an assignment problem. Okay, so you just Google up Nash. Okay, so decision theory, this minimax criterion is used, but in science and engineering, we don't normally use this. All right, weighted least square. Now I'm just quickly going over all this. So some people have a doubt. Suppose each of these measurements is having a different standard deviation, sigma 1, 2, 3, what will happen? I thought somebody will ask that question, but nobody's asking questions. So I myself have proposed this. So if the sigma I square is different, you put a weight, Wi is 1 by sigma I square, and then you can rework the regression. And the regression equations are like this. So don't try to copy this now. Anyway, I'm going to give the notes. So there is a possibility of weighting the least squares. That means those points which are having more errors will get less weight. Is that funda clear at least? So you've got the 1 by sigma I square. Is the funda clear? Can somebody confirm?
Yes, sir.
So that 1 by sigma I square is coming. So actually, if somebody is having some particular value is having a lot of error, and you know that that fellow will be thrown out. Okay, so automatically it takes care of that. All right. Now, an example of atmospheric sign. So we will do this example, and then we are done for the day. Then you earn your coffee. All right. Okay. Suppose we have 2 days. So I think see, all of you are reasonably familiar with regression, right? With linear plots and all that, correct? I can quickly go through this, or you want me to do the whiteboard work? Can somebody respond? Hello? Okay, I'll go in this fashion. Let's see how far we fly. Suppose we have 2 data sets X and Y. We want to fit a linear equation. So what this slide summarizes what I've taught so far. Here A and B are the constants. How do you obtain A and B? Minimize the sum of the squares. Dou S by dou A equal to 0. Dou S by dou B equal to 0. This slide is basically a repetition of what I have. This is a summary slide of whatever we have done so far in least square regression. Now, after putting that matrix algebra and all that, finally straight away we have given A and B. Is that okay? So this A and B, it is called an analytical solution to the least square problem. Now, if you don't do the analytical solution, you can do various combinations of A and B. You understand? Hello, is everybody with me?
Yes, sir. Yes, sir.
Now I'm telling you something very profound. So those people who are not logged in today are missing this. Okay. Watch this. Suppose you take 50 values of A and you take 50 values of B and you get 2,500 combinations, right? 2,500 combinations of A and B. For each of these 2,500 combinations, you work out the probability L. Okay. And then find out for which combination the probability of L is the highest, the maximum likelihood. That is called, what I just told you, is called computational statistics. You understand what I'm saying? So, if you have to go to Jayanagar now, for example, which is a bad idea to go now to Jayanagar at this time of the day, there could be multiple ways, right? You can go via that, you can go to Makeri Circle and then go to Vedant Sauda. That is one way. Or you can cut through Malleshwaram and go. Or you can go through Yeshwantpur, Rajaji Nagar and Pradeep Jakareddy. Are you there? Pradeep Jakareddy, are you there? Okay. Now there are many ways to go, for example. Okay. Now I'm trying to get my knowledge of Bangalore going. Okay. Now, like that, there's no need that you should always put the matrix and then put it in a box and say A and B as closed form solution. If you just freak out, just keep on calculating the value of L and find out where it becomes maximum. That is also a solution to the problem. Okay, that is called computational statistics. In order to help you do this, instead of taking random values of A and B, if you are guided, so from one A and B, how you to go to another A and B, that is called sampling. Okay, that is called, then there are many sampling algorithms. Then if you already have some knowledge of A and B, if you put it into this estimation process, that is called the Bayesian estimation. Finally. Huh? A1, B1, blah, 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 blah. A1, Bn, A2, B1, blah, 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 An, Bn. Okay. 2,500 pairs you are having. Huh? Now, if these two are the inputs, A and B, and this is your target. Target is your L. Okay. Suppose you develop, so this is basically a neural network. Okay. Now, if you develop an artificial neural network, and then for these 2,500 pairs, you know what is the probability. Now, what you do is, once you train the network, Why only 2,500? Give 2 lakhs, 5 lakhs, 10 lakhs, depending upon the power of your computer. See outside this, is there some combination of A and B which will give a value of L which is more than this? Then you are doing machine learning. Okay. But this is like taking AK-47 to just kill a mosquito for this problem. But in some cases, I don't know whether it is Y equal to AX plus B. It is data driven. I have a lot of data. This need not be L. I could have some parameters. It could be just the rain, or many of our scholars who are sitting in the wing in which I am sitting. This could be the rate of mass loss of your glacier, and this could be some parameter. And you don't have any model. Don't worry, friends. If there is no mathematics also, there is no problem. If there is data, it is like halwa. So you just take the data and then whatever you want, the target you can have. So the neural net using machine learning, you can get what is called a predictive model. So this is predictive analytics. Okay. Today I was able to give you, I didn't go deep, but I gave you the siddhant of computational statistics, sampling. If you put your beliefs, quantify your beliefs and put it into your estimation process, that is a Bayesian estimation, then brute force, just data driven, brute force, don't worry about it, don't take dou S by dou equal to 0, forget about all that. Train a neural network and use computation and kill it, and kill him. Kill him means what? Kill the problem of getting A and B, kill him. Okay, we'll say no, he nailed it, he killed it, just kill it. And then use machine learning to do this. Okay, so even for a simple, so this is the broad canvas. This is the framework in which you do probability, statistics, machine learning, Bayesian, data science, or what have you stuff. All right. Now, the Global Precipitation Mission is a joint mission between JAXA, NASA, and ISRO, as well as other international agencies, to make frequent observations of Earth's precipitation remotely from various instruments. The GPM is a part of NASA's Earth Systematic Missions Program and works with the satellite constellation to give a full global coverage. So these are the various satellites. India Megatropics is also there. Megatropics, Indo-French satellite. TRMM is the American satellite. So there are many satellites which are here. India is also partner. Now, it is a satellite observatory which orbits the Earth 16 times a day. The GPM carries 2 precipitation radars which pick up the rain signals in the Ku band and the Ka band. During one pass, it covers 245 kilometer swath with 5 kilometer footprint. Radar reflectivity and rainfall at different vertical levels are available from this precipitation radar. Now let us go back to the Chennai Varda cyclone 2016. The data with which we did some straight line fitting a couple of weeks back. Now we are saying that using the Marshall-Palmer law, the rain rate, or R, in this case equal to AZ to the power of B. Now the simple thing is using linear regression provided with this data in one scan. Data taken at different footprints in one scan of the radar. Solve the regression problem. Now we'll go through this quickly because you know this, I've already explained. So footprint up to 20, reflectivity and rainfall are given like this. Okay. Now these are the 2 columns now given to you, column 2 and column 3. Now what you do is, remember the reflectivity needs to be converted from the dBz into millimeter per this thing. There is a conversion factor, so which has been given. That's all intricate, leave that. So from reflectivity, you're going to get the Z. Now, what we are interested as statisticians is basically the last 2 columns, Z and rainfall. Once you tell me the Z, you should be able to get the rainfall. So we have to train or we have to predict. That's what you're doing. Okay. Linearize the nonlinear equation, R equal to AZ the power B. So ln of R equal to ln of A, B ln Z. Compare it with the estimator which I have told, which we already seen, A plus BX. So convert it into ln form. Okay. So this is the thing. Now you can do sigma X, sigma XY. So you know that A sigma X square plus B sigma XI equal to sigma XI YI. A sigma XI plus BN equal to sigma YI. So therefore, work out a table, do the hard work. Otherwise, you can do Excel or any other tool. So work out XI, work out sigma YI, sigma XI, sigma XI YI, sigma XI square. That's what he has done. So this has been worked out by my student Baki Harish. X square, XY, Y. So you can get sigma Y. Sigma X, sigma XY, and sigma X. So sigma X is 174, green color. Sigma Y is 36, sigma XY is 336. You can check it later. I'll give you the Excel. Sigma X square is 1544. So A is sigma Y minus blah blah. B equal to N. Okay. Now you do this. B is given to be like this, and then A is turning out to be like this. Now with this, what you do is you use your regression, substitute the value of Z and get the value of range. That you take it as a y-axis. Whatever is there in the data, take it as the x-axis. If you do a plot like this, it is called a parity plot, okay, or a scatter plot, okay, or an identity line. So this you must have experienced. So you can see that it is a straight line, but you can see that somewhere it is under predicting. Therefore, there is some other physics associated with this. Therefore, for all the rainfall rates, it suggests that one value, one combination of A and B is not good. So this is basically, it is reasonable, but we can do a little more work. All right. So I will speak for 1 or 2 minutes and then I'll close. Alternative approaches to direct estimation. Suppose we have data set which consists of a large number of independent variables. We would like to fit a model as before. However, direct solution as was presented for linear least squares requires solving a large number of equations. This is computationally inefficient. Any alternative methods are available? Yes, of course. So the gradient descent is alternative way for minimizing the cost function. We build a cost function with a large number of variables, and the objective basically is to see if the cost function is coming down to a minimum. What I have told you previously, if you've got many parameters, give some guess parameters and see what is the cost, the error, and how these guess parameters will change if you use principles of vector calculus. So all these A1, A2, A3, A4, A, B, C, basically it's a vector. So this vector, in which direction it will change, from vector calculus, you know that you have to go orthogonal or perpendicular to the existing position. So when you go in the perpendicular to the existing direction, if you go perpendicular to the existing direction, this is gradient descent. How much you go? So the perpendicularity will give you only the direction in which you move. In that direction, how much you move is by a parameter called alpha, which can be controlled by you. So this alpha is basically a parameter which you can play with to accelerate or decelerate your convergence or whatever. Okay. So whenever you achieve a very low cost value or the error, we conclude that the parameters at the state give the best fit for the model. This is the essence of a technique called gradient descent. So I think, should we stop now? It will be overload, right? If you go beyond this, what do you feel? All right. So can we stop here? Walter, what do you say?
Yes, sir.
I think gradient descent will be too much. So it's okay. I'm going a little slowly, but that's okay. So we lost some 6 people afterwards. All right. Okay. So shall we call it a day? Girish, you can stop the recording.